We'll kick off. Thanks very much for joining us this week in the second part of our discussion on heat networks and efficiencies. Yeah, just first things first, I've already sort of said it, but just in case any of you missed it, on the right-hand side of your screen, you should see a hand icon. If you can press that, that just gives me a good indication that you are able to hear me. A number of you have already done that already, so that should be fine. Yeah, so today the presenter will be Finian Parrick, the CEO of Minibems. You there, Finn?
Hi, yeah, hi.
Yeah. And I'll be moderating today as usual. Yeah, you'll also see there's a question box on the right-hand side. Warren's already used it to good effect and asked a question or made a comment. You're very welcome to put your questions in there, and I will hopefully pick them up, and so will Finn. And if they're of a technical nature, then Finn will pick them up and either answer them during the presentation or at the end. If they're easy, then I'll pick them up. Okie dokie. Yeah, just a little bit about the breakfast briefings, the Advancing Heat Network webinars that we're putting together. They're all about heat networks. The idea is to reach out to as many different people interested in heat networks, from design through to operation, and share our thoughts, as well as hopefully begin to have more and broader conversations with the market at large. So one of the key aspects of this is that we hope to make it a regular, weekly thing, and we want as much sort of collaboration, discussion with yourselves. So if you have any ideas on how you'd like to collaborate with us on this webinar specifically, or more broadly, then please get in touch. We've attached a handout to this webinar. It's a heat network performance information sheet that goes into more detail as to how we can help deliver performance on existing heat networks, which is the main theme of today's presentation. If you missed last week's presentation, you can find it on our YouTube channel. Just search for Minibems YouTube. And just a quick, I'll discuss this later on again, but next week we're having our first guest, Dave Pearson of Star Renewables, is going to be talking about the ingredients that are needed for heat pumps to work in a heat network context. And yeah, just for those of you who may be joining us for the first time and are not familiar with what we do, Minibems provides heat network performance services. Our suite of managed services include heat network optimization software that control flow rates in real time from the heat interface unit through to the energy center. We leverage our Internet of Things based data-driven approach to provide heating and hot water triage using real-time diagnostics and technical expertise. And finally, we offer comprehensive metering and billing services with both prepayment and credit billing systems available. The goal of all this is to provide unbeatable heat network performance, resulting in more efficient systems, reducing primary fuel costs and related carbon emissions, enabling low carbon technologies, and improving reliability and reducing unplanned maintenance costs. So today is the second part of 2 webinars. This week we look at how to solve the causes and symptoms of inefficient heat networks. So this is the title of today's one, Dynamic Real-Time Flow Control. How does it work? Finn's going to go into that in more detail. My job right now is just to give a brief overview and summary of what we looked at last week, which was essentially a poke around heat networks to give some clues as to what the symptoms of a poorly functioning heat network look like. And for those of you that were there, you might recall these pictures, and it's things like having very, very hot buildings, a lot of temperature going around and no control. So we can see buildings with windows open and doors open, essentially because there's no ability for the residents, or perhaps even a requirement or desire on their behalf to control the temperature in their homes. We see very commonly high flow temperatures and high return temperatures, indicating that there's very little delta T. So that's a big indicator of an efficient heat network. There's very little balancing across the radiators within flats. There's no presettable TRVs. Another clue is pumps are on at a very high speed and at constant high speed. And then, as we put it last week, museum pieces with respect to the controls. So if you're involved in heat networks, or if you manage or own a heat network, and these sorts of things are part of what's going on, then it's likely that there are symptoms there that we can actually help with. And essentially, what's happening here across these heat networks, as we find invariably, is that you're dealing with a constant temperature and constant volume. And the example is, if you look at all these customers having their sushi and the amount of sushi that's going around the sushi wheel, what's happening in these heat networks is the amount of sushi is continuing that amount and flow regardless of the amount of people that are there. So if we were to take away everyone except for the couple there in the bottom, the same amount of sushi would be going around, and that would essentially be a huge waste of resources in a heat network context. It's a waste of energy. And what we can see at a heat interface unit level is that you'll have very little delta T, very little difference between the flow and the return. So we can see on the left-hand side here of the heat interface unit, we have an 80-degree flow with 75 degrees coming back. And that is as a result of the fact that on the secondary side here, we're really not drawing off much heat. We're still delivering a high flow temperature and having a high return temperature. And a key part of delivering heat network efficiency is making sure you've got a big spread between the flow and the return. So a big difference between the temperature and the return temperature. And another aspect that a constant temperature, constant volume heat network does not account for is the fact that, particularly in Great Britain, we have very differing load conditions throughout a day, let alone throughout the year, as we can see here on this chart. Even in a day of January, you can be going from negatives to relatively mild temperatures, and you need a responsive answer to that. You need to be able to deliver the heat required, not just a constant temperature. Okay, so that is the brief little summary. Yeah, the consequence of all of this is that we have seen, and it is quite common to see that potentially up to 75% of the fuel that is being used to pass that heat around the heat network is not being used. So it's a huge waste of primary fuel. And in the case of the fact that most heat networks are driven by gas, it's a lot of carbon is associated with it as well. So that's the result, that's the problem, that's what we're trying to solve. And I'll now pass over to Finn to talk about how we endeavour to match up the supply with the demand.
Okay, thanks, Ben. Hi, good morning, everyone. Thanks for giving us your time this morning and listening in. So just to summarise really what Ben was saying, essentially we do see a lot of most heat networks in the UK running at anywhere from sort of 25% up to 50% efficiency. We don't see a lot of heat networks where we've done heat network studies for clients. The performance is above that, and in a lot of cases, it's simply that pretty much all heat networks today in the UK anyway don't have any real-time optimization on the demand side of the network. All the control tends to be in the plant room or the energy center. But of course, the thing that is controlling flow rate is not in the energy center, and I'm going to go into that in a bit more detail. So this formula here quite succinctly demonstrates what we try to do. So kilowatts equals flow rate times delta T times specific heat capacity of water. We can forget the last bit because that's a constant, 4.2. So in real terms, kilowatts equals flow rate times delta T. So most heat networks are operating at quite poor delta T's. Consequently, they have high flow rates. So high return temperatures, high flow rates. And what we try to achieve with Minibems is to increase that delta T and reduce the flow rate, which has benefits for the energy center performance and the whole heat network performance. Sorry, I'm just going to try and move. There we are. Oh. Yeah, so what we aim to do is to deliver a variable temperature, variable volume system, which means that not on the primary, well, on the primary as a consequence of the secondary, but on the secondary side of the heat network, so in apartments and in houses, in heat consumers on the heat network, we are variably delivering both temperature and the volume flow rate in order to meet the real-time actual demand of that heat consumer. And when you have proportional control between the secondary side and the primary side, that real-time flow and temperature control on the secondary has a direct impact on the performance of the primary. So if you think about how in the UK anyway, we typically have plated heat exchangers, plated heating systems on the heat network. So hydraulically separated by a plate heat exchanger. And in the flat, what we do with Minibems is we are variably controlling the temperature to the radiators or the underfloor heating system. Now, what we know is that for most radiator systems, we can consistently vary the temperature by as much as 20 degrees over the year and still heat the property. So your radiator systems, or all radiator systems, are designed for the worst case Christmas Day scenario, worst temperature of the year, typically -1 to -7 in the UK, colder temperatures in Europe. But in the UK anyway, we very rarely see those design temperatures. So you've designed a radiator for maybe 60-degree flow temperature, maybe 70-degree flow temperature, or an underfloor system indeed for 50 or whatever it might be. But that temperature is basically rarely needed. And today, most heat networks are unfortunately giving that constant temperature to properties, irrespective of actual demand. Now, the thing that's controlling that temperature is the valve on the primary side. So that valve on this on the left-hand side there, on the return, is typically what's controlling the secondary flow temperature. So what we can say is that by optimizing that secondary temperature and effectively reducing that secondary temperature over the year, we are effectively modulating down the primary flow rate to do that, or we are modulating down the primary flow rate of the heat network to achieve that. And by doing that, we significantly reduce the flow rate across the whole heat network, bearing in mind that, as I said previously, most of the year we can operate radiators at 15 degrees, 20 degrees less than the design temperature. Additionally, in the property itself, what we do is we flow control the radiator system or the underfloor system in the property itself, in the apartment itself, in order to get as much heat transfer across the emitter system as possible. So, and we don't just do delta T control, we actually optimize by calculating the real-time flow rate required in litres a minute and to optimize that flow rate delivery. And what that does is it achieves much better heat transfer in the property, so it ensures we get a large proportion of the heat that's in the pipe delivered into the room and out across the radiators or the floor, and gets us a very cold temperature here. Now, it's this cold temperature here which is cooling our primary flow temperature and giving us our low primary return temperature. With hot water, with hot water control, your problem isn't so much in-use operation. Your in-use operation on most HRUs will be pretty good, thanks to the the fact that you have a cold incoming main temperature. So in the UK, we typically have plated hot water on heat networks. So again, another heat exchanger to deliver the hot water instantaneously. And because the cold water is coming out of the ground, it's typically 10, 15, maybe 20 degrees. And so when we're running the tap, as long as we've got proportional control on the primary, which most HIUs do have, then we will get a low resulting primary return temperature. The problem isn't the in-use operation, however, which is only 80, 100 years out of the 8,760 hours in the year. The problem is actually the out-of-use operation, when in most cases that plate will be kept warm all year round on the basis that the consumer may use hot water. So what we do is we machine learn the pattern of usage of every every heat consumer, so that we can only prepare that plate and start lifting the temperature of that plate when there is evidence of historical usage. Now that does mean that a user may turn the hot water tap on at 3 in the morning when we haven't seen them do that before, but essentially the only problem with that is that they would have a delay in their hot water delivery. It's not like they won't have hot water, it just means that there's a delay, and then the machine learning algorithm would then pick that up and may, if it was consistently used at that time, would then start to heat that plate in preparation. So those are some of the software strategies that we utilize to increase the delta T on the heat consumer. And what you can see here is a chart that's showing heat meter data from a heat meter that's sat on a riser. So on the main riser coming into a block of flats, 25 flats, and here you can see the data coming out of that heat meter over 4 days. The green and the blue line are showing the flow rate and the power delivery. So you can see there's a lot of modulation of heat delivery, as you would expect, as users use more or less heat, or the load goes up and down according to outside temperature. What you can also see is that the return temperature is consistent at around 40 degrees. So irrespective of the load or the flow rate going into the block, the return temperature doesn't vary, and that's as a consequence of these software strategies operating within the HIUs downstream of that heat meter. If you then look at the same block here over a slightly different time period, a different 4 days, what you can see here is that the flow temperature into the block is 80 degrees, not 60 degrees. The previous slide was 60 degrees. As you can see here, even though we've given it an additional 20 degrees of flow temperature, there is no variation in the return temperature. It's still held at 40 degrees. Whereas normally on a heat network, if you were to increase the flow temperature by 20 degrees, you would expect to see a corresponding lift in return temperature. In the Minibems case, that doesn't happen, because we are proportionally controlling heat transfer on the secondary inside all those HIUs, and so that means that we still get that nice cool return temperature. So our control is effectively completely proportional to not only the demand but also the flow temperature coming in. So if the flow temperature increases, valves modulate down, flow rate reduces, you get even further flow rate reduction essentially, and we still maintain that nice low return temperature. So each Minibems controller that's sat inside a heat interface unit or retrofitted onto a heat interface unit, or just controlling a direct system on a communal heat network, each controller is connected to our cloud server, and that cloud server enables us to weather compensate, to parameterize things like the weather compensation heating curves. It allows us to predict failure. It allows us to observe and see performance of the unit in a lot of granularity. So we can put controllers into a 2-second data refresh mode, whereby we're seeing all the data points within the HIU on a 2-second level basis. And the data points we can see are flow rate in the heating side, flow rate on the hot water, flow rate on the primary side. We can see valve position, pump position. We can see what the pump's telling us in terms of how many watts it's using, if it's got a fault, anything like that. So we can really not only increase the yield in terms of fuel efficiency, but we can also reduce significantly the call out rates and the repairs and maintenance costs for the heat network. Also important to mention that the cloud is where the machine learning happens, and if you think about your average electronic controller, it doesn't have the processing power or the capacity to crunch a lot, vast amounts of data. So this is where we do the machine learning component of what we do, and this really differentiates Minibems from the vast array of electronic controlled heat interface units that are on the market. So it's important to say that we don't see the differentiation of Minibems as being against thermostatic or when as compared to thermostatic heat interface units. What we see is it's a different control strategy. So your average electronically controlled HIU will also be employing most of the control strategies of the thermostatic HIU, i.e. it will still be constant temperature, there won't be much optimization, it will perform as a thermostatic HIU does, albeit it's controlled electronically. Where the cloud comes into play is it allows all this visualization, parameterization, machine learning components to really have an impact and provide benefit to the system. I will say briefly that we are also working on a new project whereby we seek to utilize the heat network building estate as a thermal battery. So this is another machine learning project, and when we interface that over the cloud with a demand aggregator, we can then flex the amount of electricity use for heat pumps and CHP according to grid requirements. So we can effectively make use of low cost electricity or negatively priced electricity. Okay, so all of this stuff effectively yields an average 60% flow rate reduction compared to your constant temperature. And when we say constant temperature, what we mean is constant temperature in the flat, and more or less constant volume in the flat systems. So if you come back to that kilowatt equals flow rate times delta T, essentially what you've seen in these slides is that we significantly increase the delta T of the whole heat network by optimizing heat transfer on every single consumer on the network. And that effectively, most heat networks that we look at are operating at 10 to 20 degrees of delta T, and we are pushing that to 40 to 45 degrees of delta T. So that's where that figure comes from in terms of flow reduction, and that has a direct impact on the amount of fuel being consumed within the plant room. I won't go into on this presentation how that impacts the plant room, but just very briefly, effectively what we're doing is we are increasing the heat transfer within all the boiler plant when it is running, and we're also increasing the off time of boiler plant and increasing the off time and increasing the on time of boiler plant. And what that means is we're basically reducing the cycling of plant, and that has a big impact on fuel efficiency. This is a Sankey diagram which shows a Minibems heat network that we've done a study on recently, and it shows 12 months of performance on that network, and you can see on the left hand side the amount of energy going in. The percentage over on the very right hand side is the percentage of that fuel, that energy that went in, that was actually delivered across the heat meters into the heat consumers, i.e. on the HIUs, on the heat interface units. So that number there, 70%, is pretty good. Basically, it's about 20% above where most heat networks are, and in some cases it's 30 or 40% above where some heat networks in the UK are operating. It's still not as good as it can be, I should say, and there are a couple of reasons for that. One is you can see that this particular heat network has quite significant riser losses. 20% of the losses are on the risers, and that's because this particular heat network has risers which go up through the centre of the building, go through the ceiling voids, and then out down the external fascia of the flats and into the flats individually via the external fascia. So quite extensive riser runs essentially. But what you can see is that otherwise the performance is pretty good. There are some plant room problems there as well, which don't help the performance. but notwithstanding that, we've achieved pretty good performance there. In fact, there's a small case study on that particular project there. So it's a project using heat interface units, collaboration with ESCO controls. There are 315 heat interface units there, and there is an air source heat pump with a gas boiler in the plant room. That air source heat pump over that period wasn't operating, which is why the efficiency is where it was. With a heat pump operating, we would hope to see efficiencies of 150 or 200% with the COP of the heat pump. And I think we've got one more. So this is another site with working with Giacomini HRUs, 65 flats commissioned last year, and that's working with gas CHP and gas boilers. And I think, Ben, unless you tell me otherwise, that is the end of this this morning's presentation.
Brilliant. Yes, indeed. Well, thank you very much, Finn. There are still opportunities to send questions if you have any. I realized that I said there was a handout here, but it hasn't uploaded. So if you are interested, any of you, to have that handout, please get in touch with me directly. My details to follow. So just to talk about next week, we have Dave Pearson of Star Renewables talking about the ingredients that are needed for heat pumps to work in a heat network context. And what we're going to do with next week is we're going to follow that presentation by a brief discussion between Dave Pearson and Finian, who are sort of get a few questions together and have a sort of broader just back and forth. So if you would like us to prepare questions in advance, please let us know. Our contact details will follow. And also just please note that the time of the webinar next week is going to be from 9:15 to 10 a.m. So a bit later than we've done this week and the previous week, but it will take place both on Tuesday and Thursday. Okay, that was the questions. No. If you do have any questions, obviously, that you think of, you're very welcome to get in touch with us. A couple of webinars coming up that may be of interest to you all. Smart Cities Sweden. We collaborate, so certainly we're very much in contact with the likes of Peter Anderberg and Smart Cities. They do a real interesting set of different webinars, and the upcoming one is about heating and cooling. And also HiSoft, which is a optimization software that is going to be presenting on sustainable HVAC installations. There's the details of the people that you need to get in touch with if you wish to be part of those webinars. And yes, there are our details there. So please do get in touch.